Assalamu alaikum students. So as you know, I am Dr. Jawad Server, and today we are going to learn about no slip condition. Whenever a fluid comes in direct contact with solid, then the fluid particle that are in contact with solid sticks to the surface due to viscous effect, and there is no slip. This is known as no slip condition. If you look at this figure here, when a fluid approaches a plate, it has a uniform velocity. When it comes over the plate, it sticks, the fluid which is closer to the plate sticks to the surface. And when it sticks to the surface, it is going to have a zero velocity. And as it goes away from the plate, its velocity keep on increasing. So instead of having a uniform profile as we have seen here, it is going to have a velocity profile where the velocity is going to be zero at the surface, and as it goes away from the plate, the velocity increases, and we have a kind of profile if you look at here like this. So the velocity relative to the surface is going to be zero. The layer that sticks to the surface shows the adjacent fluid layer slows the adjacent fluid layer because of viscous forces between the fluid layer, which slows the next layer, and so on. Now this particular behavior is called as boundary layer effect, and we will discuss in the next classes about boundary layer in detail. Now the reasons for this no slip condition, reason for this velocity profile is one thing is the viscosity. As you know, viscosity is the resistance to flow, and we have discussed in the first class that the fluid particles, they always deform because of the shear force. Now this deformation and the resistance to this deformation is the viscosity. So since these layers are kind of interconnected with each other, so when the first layer is stopped, it kind of drags the next layer and the next layer and the next layer, and it slows down the velocity. That's why if you look at this velocity profile, the fluid particles which are quite away from the plate have a higher velocity, and as you become closer to the plate, velocity keep on decreasing, and right here the velocity is going to be zero. This no-slip condition can be well understood using this video. Now I will play this video, but before that, if you see here, there is a kind of ridge, and the air is flowing from this direction. This video is not playing. I will share with you separately this video, but if you look at the profile here now and the velocities by the color map, right near to the surface it is going to have a very low velocity. Rather, if you look at here, there is a kind of -4 meters per second. Just keep on looking here. So if you look at the velocity profile near to the surface, you see those blue color that indicates that there is a very low velocity, and as you go away from the surface the velocity is increasing. The interesting thing here is in this region where you see there is a blue that shows that it is kind of -4 meters per second. Now this -4 meters per second indicates that the air strikes with the surface and then bounce back. That's why it is showing as -4, because velocity, as you all know, is a vector quantity, so the negative sign indicates the opposite direction. If you look at this region here, you still see there is a negative velocity. Now remember, the fluid is moving in this direction, so there is no place around here where it is going to strike and come back to show us negative velocity, but you do see a negative velocity in this region. Why it is so? It is because of flow separation. To explain flow separation, uh, an example I use all the time is about the car. So if there is a speed bump and a car approaches it, so this is kind of wheel of the car. When it approaches the speed bump at a high speed, it reaches here at the top, and then it kind of stay above. It kind of loses contact with the surface, so no contact here. On the other hand, if the same car approaches at a low speed, then the wheel always stays in contact with the surface. That behavior where it loses contact in terms of fluid mechanics or fluid dynamics, this is called flow separation. So whenever there is flow separation, there is going to be some negative pressure here in this region, right underneath the area where the flow is kind of separated. Now, you know, when you talk about heat, it transfers from higher temperature to lower temperature. So heat flows because of temperature difference. Fluid flow because of pressure difference. And it always flows from higher pressure to lower pressure. Now since there is some low pressure region here, and then there is a higher pressure in this region, so fluid will flow from higher to the lower side, so fluid will change direction. That's why you see -4, or the velocity that is moving in the opposite direction. I hope it is clear to you, and we can discuss it when we have Q&A session. Now you can see the video. Now, in everyday life, do you see that do fluid always sticks with the surface? In most of the cases, yes, it does. For example, if you have water in the glass, you pour it out, maybe some water still sticks with the surface of the glass because of adhesion. But there is another example in everyday life, which is mercury in a thermometer. It does not stick with the surface of the glass. So you have learned in high school that there are some non-wetting fluids, there are some wetting fluids. So the opposite to the no slip condition is hydrophobicity. Now, if I just show you the video, then we can be. I think I should be able to explain it better.
Hydrophilic means water loving, and hydrophobic is the opposite of that. Now, water on a super hydrophobic surface is going to beat up, almost maintaining a spherical shape on that surface.
What we have done
is try to mimic the type of structures that we see in nature
on man-made materials. The
lotus effect refers to what happens when water, such as from rain, lands on the leaves of a lotus plant. There's no adhesion, it rolls right off. The reason for that is because the surface of the leaf is covered with hairs that are essentially on the nanoscale. And what these features do is they trap air and prevent the water droplet from being able to spread on the surface.
The superhydrophobicity that we see in nature is something that has a lot of potential applications for GE and for our customers. For example, self-cleaning materials where rolling water droplets pick up dirt and take it away, to anti-fouling materials where contaminants that are in the water don't deposit on the surface.
So these are some of the reasons why we have been really interested in the functionality and the performance that we can get from these kinds of materials.
One of the applications that we have chosen to develop for these types of coatings is related to the problem of ice. Ice is a big problem for GE and for our customers.
It's very important in the wind business where
ice build up in cold weather climates reduces the efficiency of energy production.
And today we deal with those problems in ways that are not as energy efficient as they could be if we had a passive ice-coated coating.
So that was hydrophobicity. Now, if you think about no slip condition is that the fluid sticks with the surface of the plate, and there is going to be a zero velocity. No slip condition. Hydrophobicity, fluid is not sticking with the surface of the plate. So when you are going to do simulations, then you cannot apply a no slip condition here because there is a slip there. There is no zero velocity at the interface between solid and fluid. So for hydrophobicity, we apply a slip condition. So I will repeat again, no slip condition where there is a zero velocity between solid and fluid at the interface. Slip condition, there does not exist any no slip condition. So fluid is going to slip there, as you have seen in the hydrophobicity video. The next video is about flow separation. The flow separation we have briefly discussed in a video. So in that case, now we should look at the video now.
As the angle of attack of an airfoil increases, the flow in the boundary layer stops, then reverses direction. This is called boundary layer separation. As angle of attack increases further, the point of separation moves forward on the airfoil until it has so disturbed the flow around the airfoil that further increases in angle of attack produce less rather than more lift. In this condition, the wing is said to be stalled.
So in this video, the fluid was moving from this side. Then there was some angle of attack. As the aerofoil moved from this position to upward, because of the velocity, there was a kind of flow separation. Now this region underneath the fluid, this is called wake. This area basically have low pressure. When there is a low pressure here and high pressure there, so the fluid will move in this direction. Which causes the reverse flow. Now, this is the lift, and this forces now produces drag. So although the aerofoil is moving upward, it is causing more drag now as compared to lift. And this behavior is because of flow separation. Now let's talk about classification of fluid flows. Fluid flow first classification can be viscous and inviscid. As it is clear from viscous that there is going to be higher viscosity between layer of the fluid. So in other words, when the frictional effects are dominant in a fluid flow, then the flow is called viscous flow. As the fluid moves away from the solid surface, this viscosity, like the velocity, basically increases, as we have discussed in no slip condition, that at the interface velocity is going to be 0, then the velocity will gradually increase. Or if you think about opposite way, this is the plate and the fluid is moving like this. Now the velocity profile is going to be like that: higher velocity as it goes away, and as it comes closer the velocity keep on decreasing until it becomes 0 because of no slip condition. Now near to the boundary here, there is a viscosity dominated flow. We call this kind of flow as viscous flow. As we go away, now if I go further away from here, then the velocity will kind of become uniform. This region is called inviscid region, and that flow is called inviscid flow. Now I just go back to the video where there was a fluid flow flowing over the ridge, and then you will be able to identify viscous flow and inviscid flow. Okay, what I would suggest is you can go back to the video, see it again, and then you will be able to identify that near to the surface of the ridge there is a viscosity dominated flow, viscous flow region, and as you go away there is going to be inviscid flow, kind of uniform velocity. Another classification of flow is internal versus external flow. As it is clear from the name, internal flow is when the flow is in a pipe or duct, then it is called internal flow. So in internal flow, fluid is completely bounded by the solid surface. The flow of an unbounded fluid over surface such as plate, a wire or a pipe is external flow. So I just draw a pipe here. Flow inside the pipe is going to be internal flow. Flow over the pipe is going to be external flow. Then there is sub-classification which is open channel flow. The flow of a liquid in a duct is called open channel flow. If the duct is only partially filled with the liquid and there is a free surface. So you can say something like this. Or you can say it's a river bed. And the river bed, you can say it's an open channel flow, or a canal is an open channel flow. So internal flows are dominated by the influence of viscosity. External flow, we can have both viscous and inviscid flow, as we have discussed previously. So for example, over this pipe, the flow will be something like this. 0 at the interface, and as it goes away, the velocity increases. Further away, it becomes inviscid flow. Or I can just plot it here, like this. Viscous, inviscid. Next one, classification can be in terms of compressibility. If the fluid is compressible, it is called compressible flow, and if fluid is incompressible, then the fluid flow is called incompressible flow. So compressibility or incompressibility, it depends upon the level of variation of density during the flow. If the density remains constant throughout the flow, it is incompressible. If the density changes, then it is compressible. A simple rule: liquids are typically incompressible. Gases can be compressible, but not necessarily. But here you need to remember one thing. There is no fluid which is incompressible. All fluids compresses depending upon the pressure. For example, If you apply a 210 atmospheric pressure on the liquid water, then there is a change of density of only 1%. So the water initially is at 1 atmospheric pressure. You applied 210 times more pressure, and the density of the water changes by only 1%. Now it is a very small change as compared to the change in pressure. Now the density has changed only 1%, while the pressure has changed 210 times, or in other words 21,000%. So you increase the pressure by 21,000% and there is only 1% change in density. Now comparatively, that change in density is very low as compared to the change in pressure. So for the sake of simplicity, we say that okay, liquid is or water is incompressible. But in reality, it is not. On the other hand, for atmospheric air, if you change the pressure by 0.01 atmospheric pressure, it causes the change in density by 1%. So atmospheric air is compressible. Now, incompressibility of gas flows also depends upon Mach number. If Mach number is less than 0.3, generally the gases are treated as incompressible. Another simple rule is gas flow can be often approximated as incompressible if the change in density is less than 5%. So, for example, because of the temperature, there is going to be some variation in pressure. But because of this variation in pressure, if the change in density is less than 5%, we treat that fluid as incompressible. I just give another example. For example, the air, like atmospheric air in the atmosphere, generally the temperature in the room is cooler as compared to outside. When you open the door, air flows from outside and enters inside the room. Now this flow is because of change in pressure. But if the density variation is less than 5%, we treat this behavior as incompressible. And why we are emphasizing on incompressibility? Because it makes our life easy for calculations, and we will discuss it in due course. The next very important one is laminar versus turbulent flow. So the laminar flow is generally highly ordered fluid motion is called laminar flow, and disordered fluid motion is called turbulent flow. So just have a look at the video now. Now this side you can see it's quite an ordered flow, so it's a laminar flow. This side very disordered flow, it's a turbulent flow. Now you also look at here in the center here, it has a higher velocity as compared to at the edges where there is a lower velocity. So it is going to have a velocity profile like this, something like this. Maximum in the middle, almost zero at the interface. Here there is no, for the turbulent flow, there is no velocity profile. So for turbulent flow, generally we treat it as uniform velocity. So some few rules, simple rule. The flow of high viscosity fluids such as oil at low velocity is typically laminar. High viscosity, low velocity, laminar flow. Low viscosity, high velocities, typically turbulent flows. Then there can be a transition between laminar and turbulent, and that is called transitional flow. And to determine whether the flow is laminar or turbulent, we use Reynolds number. Reynolds number is basically velocity times L over kinematic viscosity. So Reynolds number depends upon the length that is under consideration, the velocity of the fluid and the viscosity of the fluid. And remember, this is a dimensionless number. And for different fluids, there can be different values for Reynolds number for transition. Typically, for water, when the Reynolds number is less than 2300, the flow is laminar. When it is above 4000, it is going to be turbulent. And between this point, the flow is going to be transitional. Okay, so that's it for today, and house is open for questions now.